This is the last chapter that we'll be studying in Chem 214. And it'll prepare you for exam number 7, which is the last exam. And it'll be administered anytime during the exam, final exam week. Okay, chapter 18 is from my textbook. Chapter 20 is the equivalent chapter in Brown. And we're going to cover the topic of electrochemistry. So, without further comment, we'll share the PowerPoint slides and turn it into a slideshow. There we go. And that looks clear for me. Okay. Electrochemistry. What do we mean by electrochemistry? Well, I hope we have a fair idea of what chemistry is. We've been studying it for the past 14 weeks. Electrochemistry is any chemistry that involves a transfer of electrons. If electrons move from one reactant to the other, you can be assured that you're in the world of electrochemistry. So let's review some terms. Actually, this is a better definition. Electrochemistry studies the interchange of chemical and electrical energy. And that's a good expression for electrochemistry, because very often we use these types of reactions to extract energy from them. If we can intercept the flow of electrons from one reactant to another one, then we can acquire some energy from that process. But we need some common terms. When we say oxidation reduction reactions and abbreviate it to redox, it wouldn't sound right, right if we said ox-red reactions. So it's always been redox reactions for oxidation reduction. Involves that transfer of electrons. And we'll define these other terms in a minute. Oxidation is the loss of electrons. Anytime a reactant loses electrons, we say it is being oxidized. By the same token, anytime a reactant gains electrons, we say it is being reduced. And that probably comes from the concept of oxidation states, where as you add electrons, the oxidation number decreases in value. If it's positive, it'll go from like 4 to 3 to 2 to 0. It could even be negative, -1, -2, -3. Here we go. Let's check in. Okay. Just got started. Defining terms. We've talked about oxidation and reduction, and these two processes always occur together. You can't have one without the other. I mean, it makes sense. If one reactant transfers electrons, loses electrons to another reactant, then the one that lost the electrons is oxidized, the one that gains them is reduced. And those electrons, they don't exist independent of one another. In other words, they don't float around like that's physics, where you produce electrostatic charge. In chemistry, the electrons move from one place to the other. So if you have an oxidation, you have to have a reduction. And if something is oxidized, something else has to cause it. And whatever is oxidized has to be the recipient of effects from an oxidizing agent. And vice versa, anything that's reduced must be subject to the actions of a reducing agent. So it's really not that complicated. The species that undergoes oxidation is the reducing agent. In other words, it transfers its electrons to someplace else, and that reduction takes place. So the oxidized species is the reducing agent, and the reduced species is the oxidizing agent. Now, how do you remember the difference between oxidation and reduction? Well, there's a neat little mnemonic device. Oil rig, right? Oxidation is loss, reduction is gain. Okay. Now, we can set up an equation, and if we calculate the oxidation numbers for each of the species, have we already done that? We must have. Yeah, we must have already done oxidation numbers and oxidation states, but I'll give you a refresher anyway. Let's take this particular reaction. See, hydrogen ions, the manganate ion, and iron. 2+. Right? And the products are manganese 2+, 5 Fe3+, and 4 water. Okay. Remember the rules for oxidation states. If it's a pure element, the oxidation state is automatically 0. I don't see any pure elements here, so we don't have to worry with that. If they're single elements with a charge, that charge is the oxidation state. So we got a charge here, we got a charge here, here, and here. Then for calculating the oxidation states in a compound or a complex ion, like manganate, we assume that oxygen is -2. And then that means -8 total charge for the oxygens, but we have to hold one of them out for the charge on the ion. So that means you only have to balance -7 with manganese +7. So there you go. So now, well, this one is -2 and this one is +1. That's just the way water is. Hydrogen is always +1 unless we have a specific reason for calculating it as a different value. Okay, so what has happened here? Well, if you go from a +7 to a +2, what has to happen? You can't transfer protons. We know that because that'll change the element. So you have to transfer electrons. So what type of transfer will give you a +2 from a +7? You have to add 5 negative charges, 5 electrons. So if you gain 5 electrons per manganese, that will change the oxidation state from +7 to +2. Okay? So we know that this is a reduction. So there always has to be an oxidation along with it. So it looks like the oxidation is going to occur. See, hydrogen didn't change. Oxygen didn't change. Iron changed. So if we go from this iron to that iron, that had to lose 1 electron. Per iron. But we have 5 of them. So that means 5 electrons were transferred in the oxidation, right? And that's another characteristic of oxidation reduction reactions. The number of electrons has to balance. If you gain 5 electrons, you got to lose them from someplace. So 5 electrons here, 5 electrons there, that's balance. Okay. Now, we're on the way to learning how to balance redox equations. And the way we do it is we split the overall reaction into separate reduction and oxidation reactions. Since this equation is already balanced, it's a simple matter of separating out the parts of it that are responsible for the reduction and those that are responsible for the oxidation. Now, we've identified the species that reduced and oxidized, but we didn't say anything, we didn't include them in this matrix for the hydrogen in the water. Where do they go? Well, the key to that is, where's the oxygen? The oxygen's right here in the manganate. So that means water has to be in this equation. On the other side, as a matter of fact, 4 oxygens here balance 4 oxygens there. And that means we had 8 hydrogens added over here to make up for the oxygens. So now we got to put 8 hydrogens back on the other side for balance. Now, this is going in one direction. When we actually balance equations, we're going to go in the other direction. We're going to start with these and these separate reactions, and then by a prescribed method, balance them. And in doing that, we'll have to add water and hydrogens on our own. Okay, so here are the steps. It'd probably be better if I just do them. But you write separate equations for the oxidation reduction steps. Then you balance all the elements in the separate steps, except for oxygen and hydrogen. So in this case, we balance the manganese and we balance the irons. Once that's done, then you balance the oxygens by adding water on the opposite side. So with this one here, we would add a water on that side. And you balance the number of oxygens. And then with the added hydrogens you just put in, you balance the hydrogens back on the other side. And then you balance the number of electrons moved for each separate equation. Now, once you've got the electrons balanced for the separate reduction and oxidation reactions, you've got to make sure that you've got the same number of electrons in each reaction. Otherwise, you can't add them back together because the electrons have to cancel. In other words, oxidation is going to put electrons on the product side, reduction is going to put electrons on the reactant side. And they have to be equal so you can cancel them out, right? Because there are no electrons here that are visible. We did that by deduction. Okay. So there it is in flowchart fashion. And this method that I'm going to show you is for acidic solutions first. So that's where you always start. You start with balancing acidic solutions, even if the problem is to end up with basic solution. I use what I call the fake acid method. If you balance an acid solution, that's as far as you have to go. And see the protons here? That's an acid solution. But if we're going to balance it in basic solution, then there should be hydroxyls here. And the most efficient way to balance a basic equation is to balance it acidic first and then get rid of the hydrogens using hydroxyls. So I'll show you how to do that in a minute. It's really not that complicated. Okay, so we're going to say, how do we balance this equation? We've got dichromate ion and sulfite ion react and produce chromium-3 ion and sulfate. Okay. Now, this obviously doesn't have everything in the reaction mixture because that's a minus and that's a minus, where are all the positives, right? We just said that everything has to be neutral. We're not in physics. We're not electrostatic. So the cations that were used here and here against these anions are spectators. They just sit out there and do nothing, well, except balance the charge. So really the only species that we're concerned with are the active ones, the ones that are actually going to be oxidized and reduced. Okay, first step, separate this equation into oxidation and reduction half reactions. Let's see. Yeah, I've got slides for this. So here's we know that the chromium and the dichromate and the chromium ion are going to be in one half reaction, and the sulfite will be in the other one. And all you have to do, I better draw this out. Let's just do it. The slides are good for organizing things and keeping things in review, but there's no substitute for doing it step by step on the board. Bring that back over. There we go. So we got the dichromate. I better start over here. There we go. That's aqueous. In fact, everything's aqueous in this reaction, so I'm not going to put aqueous. And then we have SO3, and that yields and sulfate. Okay, so we split these into two, but how do you know which one's which? Well, you need to do the oxidation states. Right? So this one is -2 times 7 is -14 for oxygen. And then we need to hold two of them there. So that means -12 needs to be balanced with +12. Well, we've got two chromiums for that +12. Each one is +6. That's -2. And that's for the whole ion. Okay? Sulfur. 3 times -2 is -6. We've got to hold two of those minuses for that charge. So we only have to balance -4. So this is +4. There's +3. This is -8 total. We hold two out. So sulfur is +6 to balance that -6. Okay, so which one's oxidized? Which one actually lost electrons? The sulfur. It went from +4 to +6. It lost 2 electrons. So the oxidation reaction is going to look like, let's see, let me make a little bit more room here. Okay, the oxidation reaction is going to be this sulfite with a +4 on the sulfur yields sulfate with a +6 there. And the reduction is going to be the dichromate with a +6 for chromium yields chromium 3+ on that side. Okay? So we got our reactions separated, just like we do on this slide. Okay, let's balance they've already done it for us actually. We need 2 chromiums here. Let's say 2 chromiums here. Right? So that balances the chromiums. Sulfurs are balanced here. So that's the first step. Second step is oxygen. Right? So we got 7 oxygens over here and none over there. So we need 7 water. There's your 7 oxygens. Here we're adding 1 oxygen. So that means we just need to add 1 water. 1 oxygen, 1 oxygen. Oh, excuse me. My mistake. We got 4 on that side. We need 1 on this side. There we go. So there's an oxygen. There's 3 equals 4. Now we balance the hydrogens. So we added 14 hydrogens there. We'll put 14 hydrogens over here. We added 2 hydrogens here. Now we got 2 hydrogens on that side. Now we balance the electrons. So for each sulfur, we lost 2 electrons. Remember, loss of an electron in this reaction form puts the electrons on the product side. Okay? We gained electrons here from +6 to 3+. So that means the electrons have to go on the reactant side. So how many electrons? Well, let's see. We went from +6 to 3+. So that's 3 electrons for each chromium times 2 is 6 electrons. Okay? Now we need to balance the electrons between the equations. That one has 2, this one has 6. So if we multiply this entire equation through by 3, we'll get our 6 electrons, and we're proportioning the whole equation to match the electrons. Okay. So that's 3 here, that's 3 here, 3 here, 6 there, and 6 there. Now we can add the equations back together. I need a fresh marker. Okay, that's what we've done here. Well, they did the electrons first. That's all right. It works. So, yep. I'm just checking my numbers here. Okay, now we need to balance electrons. So we got 3 times this one, and then we add them back together. And when you add them back together, you're going to have the electrons cancel. You got 6 over there, and you got 6 over here. Reactants, products, they cancel. But that's not the only thing that can cancel. Let's bring everything down. Dichromate, and then sulfite, 3 sulfite, and then 3 waters, and then 14 protons. Right? So 1, 2, 3, 4, 1, 2, 3, 4, and then on this side we have 2 chromium 3+, and then we have 3 sulfates, and then we have 7 waters. Oh, forgot 6 hydrogens, plus 6 hydrogens. So that's 1, 2, 3, 4, 1, 2, 3, 4. Okay, now what else can we do? Well, we've got 3 waters here, and we've got 7 waters over there. So these 3 cancel out and leave us with 4 here. We got hydrogens also. There's 6 hydrogens here, and 14 there leaves us 8. Okay, so now the balanced equation is dichromate, 1 of those, 3 sulfites, 8 hydrogens, 2 chromium 3+ ions, 3 sulfates, and 4 water. That equation is balanced by the redox method, by the acid redox method. Okay, while I've got this equation here, let me see. Let me check my hard copies. I'm going to take this reaction as is, and I'm going to change it to a basic solution balanced equation. Because we've got it all right here. Let's see, let's clean it up a little bit. This is going to be 4. Right there. This is going to be 8. That's going to be non-existent. And there we go. Okay, now how do we make it a basic balance? Well, you add hydroxyls sufficient to convert all the hydrogen ions to water. So we've got 8 here. So we need 8 hydroxyls. And over here we need 8 hydroxyls. Okay, so these become 8 waters. All right, but we got 4 over here. Those cancel. Now we only have 4 waters. So, and then also you need to look to see, can the equation be simplified? In this case, no, it can't, because that's coefficient of 1. You can't reduce it any further. So we have one of these, 3 sulfites, 4 waters, yields 2 chromium 3 plus, 3 sulfates, and 8 hydroxyls. That means it's balanced for a basic solution. Okay? That's my fake acid method for balancing basic solutions. All right. Now, I think the subsequent slides are going to dip into that balancing technique, so we won't have to spend a lot of time on them. In this case, this says balance bromide ion with manganate ion yields bromine and manganese ion. Notice you got an oxygen here, so we're definitely going to have to add water to balance this one, and hydrogen ions also. But that's what it looks like once you get it balanced. You got a 5 here, you got odds and evens, so you can't reduce that any further. There's no way to run a divisor through there and make a smaller coefficient, whole number coefficient. So that's the balanced equation. And notice over here we got the oxygens balanced with water, and then we have the hydrogen ions over here balanced against the 16 hydrogens in water. To do the basic solution fake acid method, I've got the steps here, but I just showed you what they were, so we won't have to dwell on this slide or this one. And notice earlier we had just this part for balancing acid reactions, and then I added these green steps down here for converting it into hydroxyls. You can probably balance the equation straight with hydroxyl, but it's very tedious and it's easy to make mistakes. This method works a whole lot better, more efficient, fewer places to diverge and make mistakes. And that's what this slide is about. Okay, let's see, where's my, there it is. So if we balance this one in basic solution, we do the half reaction for the acid. Well, that's not, I just took you right to the answer. Maybe we ought to do this one. Let's see. I think we're moving along okay. Right, so we'll do one more and then we'll move on to a new topic. So here we have cyanide and manganate. And the problem with this one is I don't have any subscripts or superscripts. That's a mistake. That needs to be corrected. Okay, cyanide plus manganate yields CNO minus and MnO2. That's a solid. The rest are aqueous. Okay, so we need to determine the oxidation numbers for each of the species so we can tell which one is reduced and which one's oxidized. Right? So this one, when you got nitrogen in this situation against carbon, it's hard to tell which one is negative and which one's positive. The rule is the more electronegative one is given the negative oxidation number, and then the other one's given the positive. So if we look at nitrogen, where is it on the periodic chart? Right? Let's see. If you move from right to left, you go fluorine is -1, oxygen's -2, nitrogen's -3. So we say nitrogen, in this case, is -3. And you got to hold one of those minuses out for the charge. That means carbon only has to be +2. Okay. This one is -8 for all the oxygens. Hold one out. So we have to balance -7 with a +7. For this one, oxygen should be -2. If this one's -3, then that's -5. But we need to hold one out for that one, so it's -4. That balances, +4. So this carbon is +4. Okay. Here we have 2 oxygens, -4 total. We balance with a +4 on the manganese. Okay. Now we can tell where the electrons moved. And just a word of reminder, this determining oxidation numbers for any of these elements is a bookkeeping scheme. In other words, we're not necessarily saying that that's a charge. Sometimes it is a charge. Right? When you have a single atom that's ionized to a charge, that charge is the oxidation state. Okay, but you can use this method, and we do, for covalent compounds as well. And it's just a bookkeeping scheme to track the electrons. Okay, so oxidation is going to be losing electrons. There's +2 to +4. Carbon lost 2 electrons. It went from +2 to +4. Reduction is going to be what's left over. Manganese at +7 goes to MnO2 at +4. Okay? So let's balance the non-oxygen, non-hydrogen elements. 1 carbon, 1 carbon, 1 nitrogen, 1 nitrogen. We're done. 1 manganese, 1 manganese. We're done. Now we can move on to oxygens. We got an oxygen over here. We need an oxygen over here. Right? And then we need 2 hydrogens over here to balance them. And just a reminder, we're headed for a basic solution. So we do the acid first, then we convert it. How about this one? We got 4 oxygens here and only 2 there. So we need 2 more oxygens. Here we go. Now we got 4 hydrogens. Now we have to balance. All right. Now we do electrons. For oxidation, the electrons are going to end up on that side, correct? Right? We lost 2 electrons. Because there's only 1 carbon, we only lost 2 electrons. Here we have 1 manganese, 1 manganese. And this one, we gained 3 electrons. Okay? So now, the individual half reactions are balanced. We need to reconcile the electrons. You got an even here and an odd there. And I use the same method as I do for balancing standard equations. When you end up with that situation, you cross multiply. So we multiply 3 times this one, and 2 times this one. So 2 times 3 is 6, and 3 times 2 is 6. That gives us the same number of electrons. So this one is going to be 3. This one will be 3, 3, 6, and 6. This one is 2 times 4 is 8, and then 2, and then 6, 2, and 4. Okay, now we got electrons balanced. Before we add them together, we can just cancel the electrons. Why don't we cancel some other things too, right? On this side, we've got 6 hydrogens. Over here, we've got 8 hydrogens. So those are going to be gone. And here, we only have 2 left. How about water? We've got 4 waters here and 3 waters over here. Those waters are gone. That leaves us with 1 water. Now, when we add them back together, we don't have to do any more canceling. So we're going to have, let's see, let's start with Cn. 3 Cn minus and 2 MnO4 plus 2 hydrogens yield 3 CnO minus plus 2 manganese 4 oxide. Nothing there and nothing there. Oh, 1, excuse me. We did have 1 water left over. Yeah. Okay, so that's the acid balance. Now we need to do the hydroxyls, make it basic. So we need to add 2 OHs here, which gives us 2 water. And then we add 2 OHs over here. There we go. Now we got 2 waters here and 1 there. That one's gone, and this one is only 1. So that balance gives us 3 cyanide ions, 2 manganese manganate ions, and then 1 water, right? And then we have 3 CNOs, 2 MnO2s, and 2 hydroxyl. There you go. We've balanced it in basic solution. All right. Now to another topic. Actually, we're going to build on what we've learned so far. Up to this point, we just, here it is, we just split the reaction into half reactions for the convenience and the efficacy of balancing the equation. But there's a practical approach also to those half reactions. Notice that electrons were added to one side, subtracted from the other. In other words, you got an oxidation and a reduction reaction. If you put all those components, those reactants, in the same vessel, they'll still transfer electrons, but there's no way for you to get at those electrons if you want to extract energy from them. So the purpose of the galvanic cell is to separate those half reactions and provide an external circuit for the electrons to travel. If we can get those electrons out of the cells long enough, we can extract energy from them on their way to the other cell. And that's what we call the half reactions now become half cells for this galvanic cell. Another word for that is a battery. Galvanic cells are arranged in such a way that the reaction will go spontaneously, and we extract energy from the electrons on their travels external to the cells. Okay. Now, because, well, let's see. We got a picture. Yeah, we got a picture coming up. Let's go to the picture. So here we have our two half cells. Just focus on that first. We got one half reaction going on in one side and one half reaction going on the other side. Now, where does that reaction take place? Well, it takes place where the electrons are either lost or gained, right? At the surface of the electrode. Now, sometimes the electrode is intimately involved in the reaction. It's consumed or it gains mass. But sometimes the reaction occurs in the liquid, in the solution, and the electrode is just a conductor for electrons to move. It's not involved in the reaction. So the reactions take place at the electrodes. But in any electrical circuit, I mean, if you've been introduced to any concepts of physics at all, you cannot get the flow of electrons from one point to the other if the circuit is broken. In other words, when electrons flow here, something else has to flow back to the other side. It's got to be a complete circuit. Now, when you get electricity from the lines outside your house, they just come into the house. They don't send any back out. Well, how can that be? Well, it's really very simple. These lines are coming into your house, right? And you attach them to something here. And this machine does something. Well, those electrons are coming in. Where do they go out? They go to the earth. Power distribution systems use the earth as the completion circuit for the circuit. So they go out and they go back around, make a complete circuit. So all they need is a push. Push the electrons through, which is voltage, and then they go through the earth, call it ground, and complete the circuit. Well, in this situation, we need to do the same thing. On this smaller scale, we need to complete the circuit. So if you just have this electrode over here connected with a wire to that electrode in the half cell, nothing's going to happen. You need a way for the charges to move. That's what the salt bridge is for. So you have, usually, not always, but usually you'll have a plug here, and you could have liquid in there, as long as the plug was secure and it did not allow the salt bridge components to mix freely with the half cells. Sometimes we put auger in here. We mix our salt in with the auger, and that stabilizes it, but it allows the electrons the ions to move and transfer charge. In fact, I've got a video coming up that will explain that probably in better fashion than I have. Or the other thing you can do is put a porous disc in here between them. And that way you don't need any salt bridge. That porous disc will allow ions to move, but it won't allow the half cells to mix, because you don't want them to mix. If they mix freely, then those electrons are going to take the shortest route, and that is straight from here to here, not external. You want them to go external so you can extract that electrical energy. Okay, so we got to decide which one has which reaction in it. Okay, this slide tells you exactly what I just told you before, so I'm not going to stop there. All right, one side hosts the half reaction for oxidation. Okay, that side is called the anode. The anode is where oxidation occurs. Right? And you can see by the electrons moving away from the solution, oxidation occurs on this side. Right? It's losing electrons to the circuit. And on this side, they're showing up on this side for the reduction step. This is called the cathode. Okay, so the cathode is here, anode is there. Just memorize it. The way I make sense of it is the cathode is the one where electrons arrive and they attract cations. That may not be what the reaction is all about, but it's the way I rationalize it. The cathode is where the electrons arrive and they attract cathodes. But by definition, the cathode is the site of reduction. Okay. So once you get these connected, you can measure a voltage in that external circuit. And the voltage is akin to push. What's driving the electrons forward? We can measure that voltage. It's often referred to as EMF, Electromotive Force, is what's pushing the electrons. Or cell potential. Now this fancy script E with a subscript of cell. These are kind of hard to come by, so sometimes you just see a plain old capital E. The units of measure, of course, are the volt. And the volt is equivalent to 1 joule of work per coulomb of charge. Okay, that's a coulomb of charge. It's just a measurement named after its discoverer, Coulomb. He's a Frenchman, I think. And then the joule for energy, which means work, right? How much work can you get for this much? If you can get a whole lot of work for a small amount of charge, that means big voltage, right? If you can only get a little bit of work out of a lot of charge, that's low voltage. So that's why if you have a lot of heavy lifting to do, a lot of work to be accomplished, it's best if you attach your equipment to a high voltage source. So around the house, you'll have, most things will be 110, 115 volt, right? That's typical. Or you might have some heavier work to be done, and there'll be 240 volts or 220 volts, like your washing machine or your dryer or your heat pump will be on a higher voltage. Industrial applications, you can have equipment that runs on 480 volts, or even higher. Okay, so that's the definition of a volt, and we'll talk about it a little more later. But here's your video. You might have to turn up the volume, because for some reason when I embed these videos in my PowerPoint slides, it decreases the volume. So I can correct that in the recording, but for now you may have to turn up your voltage. Turn up your volume.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. Two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay, I thought that was a pretty good explanation. So, how do we actually measure this voltage? This is a physics problem, actually. Well, there are two methods. One's called the voltmeter, and the other is the potentiometer. They use two different methods to determine the voltage of in a circuit. In the voltmeter, they actually allow current to flow through the circuit and the meter, and it is allowed to traverse a resistor. Right? I'm using terms this is basically physics. So I don't expect you to grasp the entire. I want you to see the difference between the two. So the key is that in the voltmeter current, electrons actually move. In a potentiometer, they don't move. Okay, here's how they do it. With a voltmeter, if the current is moving and you pass it through a resistor, then you can do some calculations and determine what the voltage is. They use Ohm's law to determine the voltage. Hold on, I'm thinking. The Ohm's law is an expression of how much current flows through a resistor with a given voltage. So if you say hold on a second. Voltage now is equal to the flow for a given resistance. No, it's the other way around. There we go. So this is the resistance, and if they measure the flow through the meter circuitry, they can calculate the voltage. The key is that for a voltmeter, you have to allow electrons to flow. So by way of, remember entropy and the maximum amount of work that you can obtain from a process. In order to get the maximum amount of work out of a chemical process, you need, or actually a physical process also, you need a reversible reaction. In other words, it's got to be very small increments. It can go either direction. That's how you get the maximum work. Well, you can't measure the maximum work out of allowing the full flow of electrons through the circuit, right? That's irreversible. So the way you measure for maximum work, and remember, voltage is a measure of work per unit charge, is you apply potentiometer. And there what you do is you adjust. There's in the circuitry, you have a calibrated voltage. It's an active circuit. You can apply reverse voltage against the incoming voltage from your galvanic cell. And once they balance, then there are no electrons moving. And you measure the voltage that it took to balance that force, right? So there you're at a reversible situation, and that voltage is an expression of maximum work available. So in many respects, the potentiometer is a better device, but they're more expensive. So we generally use the voltmeter. Or if you buy one in a store, it may come with other functions, and they call those multimeters. Okay, I spent a lot of time on that slide, probably more than I should have. Okay, so here's a digital voltmeter, and it's measuring the voltage of this, I don't know, it could be zinc and copper on the other side. But we need some way to compare the voltages of half cells, because suppose instead of putting zinc here, you want to put and copper over here, you want to put silver and form a different galvanic cell. Well, it'd be nice if you could predict what voltage you would expect from that reaction. Kind of like Hess's law, where you combine reactions to get an enthalpy for the target reaction, just so that you don't mess with a reaction that could blow you up. But here we would like to know in advance what voltage we should expect. And then when you actually measure it, you can say, all right, why is it different? That type of. So the problem is that half cells don't produce their own voltage, right? They only produce voltage in a circuit, right, against another half cell. So what we had to do was settle on a standard half cell to which all other half cells are measured. Then once you've established a voltage with the standard half cell, then you can make some predictions on combining two half cells that are not connected to the standard cell. So here's the result of those measurements. It's called the standard reduction potential. So what that means is that all the reactions in the table of these accumulated voltages are written in terms of reductions. So if we say zinc 2 plus 2 electrons yields zinc metal, that would be a reduction reaction. And the voltage would be given out here in some values, okay? Either positive sign or negative sign, against the standard potential. I'll talk about the standard in just a second. But the reduction potential here with that little zero means under standard conditions. And those standard conditions are the solutes in solution are 1 molar concentration, and if there are any gases introduced, they have to be at 1 atmosphere pressure. Also, I left something out, didn't I? Oh, it's coming up. Now, it's on the next page. But the temperature has to be 25 degrees Celsius. So those are standard conditions. And all these half reactions are written as reductions in the tables. All right, now here's the kicker. What are these half reactions compared to, right? We need a standard cell. Well, they're compared to the standard hydrogen electrode. So the standard hydrogen electrode is, let me see, do I have a picture of it? No, there's no standard. The standard hydrogen electrode is like this, and it's got water plus, I think there's some hydrogen ions, so they'd have to be 1 molar hydrogen ions in that solution. And then you have electrode down here, and there's a wire, there's a piece of platinum right here. And then you have, from this source, you have hydrogen gas at 1 atmosphere pressure, and it's coming through here and it's bubbling right there. Okay, that's your half cell, the standard hydrogen electrode. Now, when it's hooked up to some other process, it could be the anode or it could be the cathode. It just depends on which one it's connected to. But in any case, this one is given a standard half cell voltage of 0 volts. Okay? Now, we know that it has a potential of its own, but in circuitry, we set it at 0, so everything else is compared to that. So then you can compare 2 other reactions, and then the difference there that you see between those reactions is it's all relative. It's a change in voltage. So it really doesn't matter what this one is. We could have made this one 10 volts. Doesn't matter. Because once you start comparing the others, it's the difference that matters. Okay, so that standard hydrogen electrode is used to compare all these values. And let's see. What do you do when you combine 2 cells? They can't both be reduced, right? So if you have another one, like copper, right? Reduction potential. Then you got to decide which one is going to be the anode and which one's going to be the cathode. The cathode is the one that stays just like it is. Right? This one's going to be oxidized, so it has to be flipped. It's losing electrons. So this one would become zinc yields zinc 2 plus 2 electrons. And then the voltage that you have here would now become, change the sign. Okay? That's what you do when you flip the reaction. Now when you combine these 2 together, you get an overall voltage for the 2. Okay, if we have to multiply a half reaction by an integer, in order to balance the equations, it has no effect on the standard potential, because the standard potential is an intensity factor. It doesn't matter how much of it you have. It's always the same. So that's good. You don't have to change the amount of standard potential if you multiply your equation through by your half reaction through by any value. Okay, now which direction does the reaction go? It goes in the direction where the overall voltage for the cell, when you combine the two, is positive. The positive volt tells you what direction it's going. All right, this came out of my textbook. It's in 2 slides. Notice that you get these voltages here, positive, 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 all the way down to 0. Right? So here's the hydrogen, the standard hydrogen potential, set at 0. So then you go down and past this, they start getting negative, and they go big negative. Okay, so here's your copper right there, and your zinc should be over here somewhere. Let's see. Oh, it's on the next slide, excuse me, because this goes down to 1.23, and then the next column is 1.21. So zinc is where? Zinc is right here. Right, minus 0.76 volts, measured against the standard hydrogen electrode. And then the copper is measured here against the standard electrode. So in this case, well, let's just learn how to use it. Okay, so there are 2 ways to determine the potential of a cell. The way that most chemistry courses teach it is they just give you this formula and you're on your own. The potential of the cell is the reduction potential for the cathode minus the reduction potential for the anode. And it makes sense. If the reduction potential is here, you just leave it alone because it's the cathode. But if the reduction potential is here, it's the anode, so it's got to go the other direction. And that's why the minus sign, because you have to change the value, change the direction. And if you do this formula, then you get the standard potential for the cell. The way I like to do it is I write the half reactions and I say, for this reduction, is this going to be the reduction? If it's going to be the reduction, leave it alone. Just put the value out there. Or if you write this one as reduction and you put a value out here, then ask yourself, when you add those values together, are you going to get a positive or a negative value for the total? If you get a positive value, then you wrote them correctly. Anode, cathode, cathode, anode. But if you end up with a negative value, that means they have to be flipped. You got to turn them back the other direction. Either way works. Just whichever way you feel comfortable. Okay. So here's an example. If we're going to have iron 3 plus to iron 2 plus in one half reaction, and then copper to copper 2 plus in the other cell, then what are the reduction potentials for each? Well, the reduction potential for iron 3 to 2 plus is 0.77 volts. And the reduction potential for copper 2 plus to copper is 0.34 volts. But notice we're going here from copper solid element here. So that one's lost electrons, it's oxidized. That's the anode. So the anode has to be converted, has to be a negative. Right? This is reduction. We need oxidation. So that would be a negative 0.34 here. Add them together. Right? And you get, where is it? 0.43 volts for that cell. So there we just identified which one was the cathode and which one was the anode based on the overall reaction. And that meant the anode had to be reverse symbol. Then you could add them together. If it was me, I wouldn't even need that equation. If these are the two half reactions, I would say, all right, if we, let's see. Oh, okay. Decide which one needs to have its sign changed, right? These are both reduction. Can't be both right. One of them's got to be an oxidation. So if we change this one, if we made this one the oxidation, that would be a negative 77 and a 0.334. You get a negative number. So it can't be that. It's got to be the other way around. So this one's reduction. That one's oxidation. So now this one is minus 0.34. And then you get your voltage. Personal preference, whatever works. Well, now the standard potential for our reaction doesn't matter whether you multiply your half reactions by a constant or not. But very few actual laboratory galvanic cells are built at 1 molar concentration, 1 atmosphere pressure. They're usually 25 degrees C. But that concentration difference makes a difference in the voltage that the cell actually produces. So if you have a 1/10 molar instead of 1 molar, then you're going to have a different voltage. So we need a way to tell how to do that. Let's see, am I there yet? This will come later. We'll see the quantitative transfer of electrons must be considered. In other words, when you balance the equation, like we did before, then you know how many electrons are actually transferred. In one case, I think we had 6 electrons transferred. You need to remember that number. You need to find out what it is and hold it if you want to know the actual voltage that's produced in your cell. We're going to use an equation called the Nernst equation. And we'll talk about it in just a minute. And it is an equation for converting standard potential into actual potential based on the concentration of your reactants. Also, I haven't mentioned this before, but when you set up a galvanic cell, it's going to run in one direction only. That's the spontaneous direction. But you can make it run backwards. All you have to do is, if the voltage of the cell is 1 volt, then all you have to do is external source supply a voltage that's greater than 1 volt in the opposite direction. And you can force the reaction backwards. That's called electrolysis. Okay, so you just have to have an energy source external to your galvanic cell, and now you turn it into an electrolytic cell. Okay, this is kind of a weird problem. I kept it, but it's going to be difficult to follow. You've got these species. We want to arrange them in order of strongest to weakest oxidizing agent. Remember, an oxidizing agent is any species that is reduced, right? Because it draws electrons to itself, causing something else to be oxidized. So we need the one that is most easily reduced. That is, it has the highest voltage available for the reduction equation. Now, here's the problem. We have reduction potentials for fluorine, and we have reduction potentials for sodium. No, we don't have reduction for fluorine. We have reduction for sodium and chlorine. Sodium ion, excuse me, sodium ion and chlorine. So the reduction potentials for sodium would be like this, right? We can get that right out of the table. Or they also have one where you can do this one. Like that. Let's see, we would need 2 electrons. Okay. Those reduction potentials are right out of the table. But we don't have reduction potentials for sodium metal, right? What would that look like? Sodium plus an electron yields. That's not going to happen. Sodium's a metal. It doesn't want another electron. Or iron. Iron's the same way. Fluorine, excuse me. Yeah, iron also. Iron plus electron. Or fluorine ion. Try to add another ion to that. Right? None of those are going to work. Right? You won't have a reduction potential for these that is worthy of discussion. So really what we're doing is comparing these two to find the strongest oxidizing agent. So really only need to look at those 2 values. Okay. So let's see. Right, we can't know that one. I already showed you. That one is 1.36. Yeah, that's good. And we know the sodium ion. So it's this one minus 2.71, which means it's not spontaneous. It doesn't want to go that way. But chloride is a very good reducing, oxidizing agent. It will accept electrons. So chlorine is the strongest oxidizing agent of this group, the chlorine molecule. There you go. So chlorine is better than sodium. Those are the only 2 that we have values for. The others, I just sort of stuck them in there in any order. This makes sense, though. How are you going to add an electron to a negative ion? It just doesn't want to go. The others are based upon their behavior as metals. Sodium is more active metal, they say, than iron. So sodium is more likely to reject electrons than iron is. So that order is probably iffy, but these 2 are definitely right. Chlorine is a better oxidizing agent than sodium ions. Okay, now when we construct these cells, we could draw the whole picture out, right, with our cell and our salt bridge and all that. But for efficient production, you would need graphing software incorporated into your word processor to generate any kind of a document. So we've, well, somebody came up with line notation and agreed upon how you would write it in a linear fashion as a description of the electrochemical cells, the galvanic cells. We always start with anode components of our cells listed on the left-hand side. That's oxidation first. And then the cathode is on the right-hand side. And we string out those values like this. Now we need some way to identify what type of separation there would be between each of the components. So that comes next. If there's a double vertical line in there, that indicates a salt bridge or a porous disk. That actually separates one half cell from the other. If there's a single vertical line anywhere, that simply means that there's a phase difference between the two components that are listed. Right? So we need an example, don't we? If we don't specify, then the concentrations are assumed to be 1 molar. But if you know what the concentrations are, you should put them in there in parentheses with the component. Right? So here's an example. Here's the cathode side. There's your double line. Right? That's the salt bridge or the porous disk. And then this is the anode half cell. Magnesium in the anode is being oxidized to magnesium 2+ ion. Okay. On the other side, aluminum, this is the cathode, aluminum is being reduced to aluminum metal. Right? So electrons are flowing from this side to that side. And we wrote what phase they were in. Notice there's a phase difference here between solid and aqueous, so there's a vertical line there. Same over here, a vertical line there. That separates phases. Okay. That's line notation for electrochemical cells. But like I've mentioned earlier, there are some situations where the reaction takes place entirely in solution. And in that case, all you need for either that anode or that cathode is a conductor, an inert conductor that you place in solution, some way for the electrons to get in there or leave. In the laboratory, sometimes we use platinum, right, because it's totally inert. In large industrial settings, they might use graphite because it's a lot cheaper. And it's replaceable, right? If the graphite erodes over time under harsh conditions, they can just pull it out and stick a new one in. But it needs to be chemically inert and a good conductor to be a non-participant in the half-cell reaction. Okay, so let's say we have these two half cells, right? Silver and iron 3. And we want to describe the galvanic cell based upon these reactions, all right? We have to decide which one's going to be the anode and which one's going to be the cathode. Well, look what happens. If you change this reduction to an oxidation, you get a negative number that's too big, right? You come out with a negative value when you add them together. So it has to be the other way around. This one's reduced and this one is oxidized. So we flip this reaction, make that negative, and that says this is the cathode, this is the anode. There you go. So we have to run this one in reverse to make it the anode. And that means the difference in voltage is 0.03 volts. That's not much, but it is there. It's real. And there's the balanced equation. Now notice, for later use perhaps, we've transferred only one electron. Okay, so keep that in mind. And this is the overall reaction. So, let's see. Are we going to draw it? Yeah, there we go. So, by convention, we use the same convention in actually drawing the diagram as we do in line notation. The anode goes on the left, cathode on the right. So the electrons are always moving from left to right in the external circuit. And there you have your silver. And the electrode here is intimately involved in the reaction. But over here, iron 2 plus and iron 3 plus are in solution, both of them. So all we need is a way for the electrons to escape. Right? So we use a platinum electrode there. Okay, notice also what's happening. If we send electrodes over here to reduce silver ions, what's going to happen to the mass of that electrode? Over time, the mass of that silver electrode will increase because you're taking silver ions from solution and plating them on this silver electrode. Okay? Now, I would venture you could put a platinum electrode over here also. It delivers the electrons to this solution, reduces the silver ions to silver metal, and they would actually plate on the surface of that platinum and increase its mass. And you could measure that increase of mass and make some calculations, stoichiometric calculations on the reaction. Okay. Let's see. Now, we haven't mentioned any of the counter ions in here, right? This has got to have some anions, maybe chloride or sulfate, whatever the case may be. This side wouldn't be chloride because silver chloride is insoluble. So it's probably nitrate. Silver nitrate would be a good choice here. And we can make nitrate on this side also, as long as they're soluble. Now the line notation would look like this. You have to include the platinum, and there's a phase difference between the platinum and the iron ions, right? But they're both in the same phase. So we just put a little comma in there to show that they're in there together. And then there's your porous disk, and then you have silver and phase change, silver solid. So that would be your line notation for this diagram or this graphic of the galvanic cell. Let's see. All right. This is just a summation of the description of a galvanic cell. You got to determine which is the anode, which is the cathode, and then the cell potential is calculated based on those changes that are needed. This one won't change because it's the cathode. It's a reduction potential. This one has to be flipped, made a minus, before you add them together. And you also want to know how many electrons are transferred in the process, and that'll come in the next couple of slides. And then when you write the line notation, you need to make sure that you have written it correctly with salt bridges or porous disk, phase differences mentioned, any concentrations that you may know in advance. So for these two, this is what the description would look like. I used a drawing program for this. This copper and copper ion side, this half cell, is going to be the anode. So that means electrons are going to move out of here, and the copper is going to be ionized, converted to copper ion. So the copper ion concentration will increase, and the mass of the electrode will decrease as electrons are moving through to the other side. And now we're going to deposit silver onto that electrode. Its mass will increase. And that means that This voltage you leave alone, this voltage you flip. Add them together. So this is the voltage for silver side. This is the negative voltage for the copper side. And the voltage the maximum voltage obtainable is 0.46. I shouldn't say maximum. I should say this is the standard voltage under standard conditions, 0.46 volts. Okay. What happens? Let's use Le Chatelier here. What happens if we take this half reaction here? Right, for the anode, it's going to be copper is going to be oxidized, so it loses electrons. So this is the half reaction for the anode. What happens as the copper ion concentration is increased? Right? As you increase the copper ion concentration, Le Chatelier says the reaction is going to try to go the other direction, which means electrons are not going to be pushed into the circuit as much. So as you increase the copper ions on this side, you gradually decrease the voltage until it's zero. So mathematically speaking, the actual reduction potential of this side increases to the point, because reduction is the opposite direction, reduction potential increases to where it balances the oxidation potential, and that's when the cell shuts down. Otherwise known as a dead battery. Okay, so why do we want access to these electrons in an external circuit? Because we want to do work with them. We want to do something with them. Right? Maybe we want to turn on a flashlight, or run a blender, or wash our clothes. Whatever it takes. So, unfortunately, the cell potential and work have opposite signs, right? By definition, right? What happens with the system? If the system does work on its surroundings, which is what we want to do, then the sign is negative. But the sign on the cell potential is positive, right? So we got to reconcile that. So we just change the sign, right? We add a negative to the W. There's joules per coulomb, right? Like I said earlier, the definition of voltage is joules per coulomb. But in order to actually use the measured voltage in terms of work, we need that negative sign so that they're both compatible. Otherwise, this positive voltage wouldn't jive with a negative work potential. So if we just solve it for work, we have Q times E, negative W. If you're going for W, then you move the negative to the other side and say, okay, what's the voltage? How much charge moved? Multiply that together, then take the negative sign, and that will be work. There you go. This is the maximum amount of work available from that electrochemical cell. Negative QE. Now, when we were doing, this is first semester, thermochemistry, Q was heat. But when we're talking about physics and charge, Q is meant to be charge. So this is the number of coulombs times the voltage yields work in joules. Okay, so that's how those values, those units of measure, are equivalent to one another, right? Negative coulombs times voltage. coulombs times voltage, negative sign equals joules. And the joules, it could be negative sign too. If you're doing work on the surroundings, then it would be negative. Okay, this is just a refresher, right? Volts, joules, coulombs. Volts is a measure of the work performed per unit charge. Okay, let's see. I must have left a slide in here. Oh no, okay. In any of these spontaneous processes, some energy is always wasted. I mean, we learned that in the last chapter with discussion of entropy, right? You can never get everything out of the process. Some of it's lost to entropy and some of it's lost to inefficiencies. But this is the maximum value that you can get. And then you should expect something less than that for the useful work minus some losses. So if we want to know the actual work that's being done, rather than E sub 0, we need the actual voltage and the charge transferred to find out how much work is actually being done. Right? So for that, we need to know, since chemical reactions are the standard currency for chemical reactions is the mole. So if we're going to transfer a mole of electrons, what is that equal to in terms of charge? Well, here's your conversion factor. It's called the Faraday. The Faraday is 96,485 coulombs per mole of electrons transferred. That's what that charge means. So that conversion factor, you need to, well, it should be available in the useful information in the same folder where the exam is located. So you just need to have that available for you so that if you need to do these calculations, there's the number. Coulombs is a product of physics. And moles, of course, is a product of chemistry. So this is the conversion factor that bridges the gap. Okay, now we're going to sort of tie in chapter 17, or my chapter 17, with electrochemistry. We talk about free energy. Remember Gibbs free energy, the delta G value. The delta G is an expression of maximum useful work that can be obtained from a process. Right? There it is. W max equals delta G. And they're the same signs, right? Delta G, you're getting work out of the system, like work out of the system, free energy out of the system. So their signs are compatible. For a galvanic cell, we know now that maximum amount is available if you know the charge and the electrical potential of the cell. And then, of course, you have to apply a negative here in order to make them compatible. Well, we just said by the transitive property, if A equals B and A equals C, then B equals C. Right? So they're all equal. Now, the charge in coulombs is equal to the number of moles of electrons moved times the Faraday. Right? There's the Faraday, because we go back, 96,485 coulombs per mole. Okay, so there's your Faraday. If we multiply that times the number of moles, what do we get? We get charge. We get Q. That's why this formula works. Q equals number of moles times the Faraday. Okay, so if we take this expression and we substitute for Q, we substitute moles times the Faraday, then we get this expression, minus moles times Faraday times cell potential is equal to delta G. Okay. Oh, there's Michael Faraday. I found this painting. He was let's just say it, he was a brilliant experimentalist. He could design experiments, particularly in physics, to tease out information from a problem better than anybody in his day. Some of the instruments he came up with were just, they boggle the mind. And he used them to answer questions. Okay, so now that we have delta G equal to minus N Faraday standard potential, then the standard free energy is equal to that value. All right, what does that mean? Well, we know that a negative delta G is spontaneous. Right? So that's positive, and that's positive. So with this negative out there, that means this negative G is equal to this, is related to this positive voltage. That's why spontaneous reactions occur with a positive voltage. And if you run it in reverse, of course, you're going to change this to a positive and change that to a negative. For the electrolytic cell, where the external potential drives the reaction backwards. Okay. Now here's another concept. I'll leave that there. The concentration cell. Notice in this situation, it looks like we've got the same half cell on both sides. The difference is concentration, right? This side has 0.1 molar silver, and this side has 1 molar silver. So which way is it going to run? Le Chatelier says that we're depleted in silver ions on this side, so we need more of them, right? If we say, let's see, that's the anode. Silver yields silver plus electron on this side. And then on the cathode side, you have this one. Like that. So Le Chatelier says, if you've got, if you're depleted in silver on this side, and you got more here than you do there, then the reaction is going to run to supply more silver ions in solution. So the reaction is always going to run from the low concentration to the high concentration, delivering electrons. And what does that do? Well, it increases this one, silver ions, and it decreases these silver ions. So it runs this direction and that direction together. Until when? Until you balance the concentration. So at some point, you'll have an equilibrium situation. In other words, you'll have enough over here, don't want any more, and you will have depleted enough over here that it can't take anymore. So at that point, now the voltage is 0. But what is the standard potential for this cell? Remember, the standard potential is based upon 1 molar concentration. The standard potential for the concentration cell is 0. The actual concentration is what we're after. Okay, so we leave it to Walter Hermann Nernst. There he is in his younger days. He was a German chemist. He dabbled in a lot of stuff: thermodynamics, physical chemistry, solid state physics. He proposed a formula that eventually led to the third law of thermodynamics, and he got a Nobel Prize for it in 1920. But we're studying his Nernst equation, so we need to get to that. Okay, what it does is it gives the relationship between concentrations of cell components and relates those to the standard potential so that you can calculate the actual potential. Right? And here it is. The actual voltage of the cell is equal to the standard potential minus gas constant, temperature in Kelvin, divided by moles and the Faraday. And you multiply that times the natural log of Q. And we know Q, right? K is the mass action calculation for an equilibrium reaction. Q is similar to that, but it's not equilibrium, right? If it's equilibrium, then there's no voltage anyway. So we need Q. What are the concentrations? Like before, we had 0.1 molar and 1 molar, correct? For our concentration cells. So this is what the R is equal to. There's your Faraday again, temperature in K, moles of electrons transferred. That's why we need to know how many moles of electrons are transferred in the cell reaction, because it goes right in there. But that's kind of an unwieldy. This works for any temperature, any number of moles, and whatever Q you calculate. Well, and the standard potential. But in most cases, the temperature is going to be 25 degrees, so we can plug that in. And the Faraday we know. We just need to know the number of moles and the R. So we can combine R, T, and F together into a single constant, right? Here, here, and here. But natural log is we can use it, but it's easier to deal with common log. So here's the correction for common log. If we multiply 2.3 times the common log, that's equal to the natural log, right? So now that we've made that substitution, we can just take that 2.3026 and put it over here with these others. And now all of these together become 0.0591 divided by the number of moles of electrons, and then the common log of the Q. That's a lot simpler, easier to work with. Now, this little blue box over here, it just proves that I didn't just pull this out of thin air, 2.3026. This is the proof that that conversion is true. Natural log of Q is equal to this value here. And you can look at it at your leisure if you care about it. It doesn't matter. What you need to focus on is this equation right here. That's the modified Nernst equation for 25 degrees Celsius. Okay. So, like I said before, we can do that calculation and determine the actual voltage of the cell. But it doesn't just stop there. We can use this equation for other purpose. What if the system were at equilibrium? Right? It doesn't have to be a concentration cell. It could be just, zinc and copper. You could calculate the Q for that reaction, right? The copper solid and the zinc solid would drop out. They don't belong. because in an equilibrium expression, they're eliminated. So we just calculate the Q for that reaction based on the copper ion concentration and the zinc ion concentration, and then the number of electrons transferred and the standard potential for the cell. That would give us the potential for that cell. But what happens if the system reaches equilibrium? The battery's dead. Now there's no voltage, right? That E becomes 0. The standard potential is still the same. And then if we know the number of electrons, we can plug those in and the standard voltage and calculate the K for that reaction. So the standard voltage is equal to this expression with K instead of Q. So if you know the standard voltage and you know the number of electrons transferred, you can calculate K. Or you can go any way you want to, right? All you need is one unknown and you can solve for it. That's another way to arrive at the equilibrium constant for a reaction if you measure the voltage. If you determine the standard electrode potential, the standard potential for that cell and the number of electrons, you can calculate K. It's just another way to get that value. Okay. Oops, I went backwards. All right. So here's an example. SF406 2-, which is probably another polyatomic ion, and S203 2-. I think this is thiosulfate ion here. I'm not sure about what that one's called. Dithiosulfate. It looks like it's 2 of each. But with this reaction, you can oxidize chromium 2+ to chromium 3+. Right? So there's your reduction potential there, but this one's going to have to be the anode. Right? Because if you make that one the anode, you get a negative number. So we got to convert this one to a positive and add them together. That gives you the standard potential. Okay? So, and how many electrons move? Well, let's see. We got to balance this one, so 2 electrons move. Right? So N equals 2. There you go. Balance the equation. There, we did that. There's a standard potential, 0.67 volts. N equals 2. So if we rearrange the equation, right, and put log K over here, then since actual potential is 0, let's see. I kind of jumped there. So if we say, where is it? There it is. If we say this one equals 0.0591 divided by N log K, right? Then if we solve for K, we just say log K equals E sub 0 times N divided by 0.0591. There we go. So that's where they got that equation. Let's see, get back over here. Now we just substitute 2 in for this, the standard potential, which was 0.67, right? And then divide by this, and we get 22.6 is log K, right? Then we resolve that into actual K. So then we would say E to the 22.6 equals K. There we go. And the K for this reaction is 4 times 10 to the 22nd power. Now, what does that mean? That means that the reaction is at equilibrium is way, way to the right. And that's not unusual for electrochemical cells, for galvanic cells, to have a K that large. So what's the difference between E and E0? Well, E0 obviously is standard conditions, and E is actual value. When is E equal to 0? When the cell is at equilibrium. It's a dead battery. When is E0 equal to 0? For a concentration cell. E0 is based upon the standard cell potentials for the anode, let's see, for the cathode minus the anode. If the standard potentials are the same, if there's the same reactions, then E0 has to be 0 for a concentration cell. Okay? Let's see. I know I've gone way over. Okay. Let's say a concentration cell is constructed using 2 nickel electrodes. So we're going to have a nickel in the electrode inserted into the solution and nickel 2+ ions in solution. Okay, one of them is going to be 1 molar, which will be what? Well, versus 10 to the minus 4th molar. Which one's anode, which one's cathode? The low concentration is always the anode. And the high concentration is the cathode. So the 1 molar will be on the right, 10 to the minus 4th molar will be on the left. Okay, so let's write these equations. Well, this one's going to be the cathode reaction is a reduction. The anode reaction is an oxidation. We put them together, and we've got these little subscripts to tell us apart. Then what is the Q value for this reaction? Well, the Q is going to be this anode concentration divided by this cathode. This anode concentration divided by this cathode concentration. So what does that look like? Well, there's the nickel 2+ concentration in the anode, which is 0.0, well, it's 10 to the minus 4th molar, and then 1 molar down here. So there you go, right there. And then you need the number of electrons, which is 2, right there. And you can calculate the voltage for this cell, maximum, would be 0.118 volts for this concentration cell. So that also illustrates that as the cell runs, the concentration of the anode ions increase and they decrease for the cathode. So you start to decrease that log term, and that decreases the voltage, eventually down to where it's 0. Okay, let's see, what do we do? This one, a nickel electrode in one at 1 molar and a silver at 1 molar. These two, oh, which way does it go? Well, let's change this one to a negative. Let's make the silver electrode the anode. Won't work. Both negative, that's not spontaneous. So that means this one has to be the anode, and we change it to a positive 2.23. Add them together is 1.03 volts. So this is the anode side, which will be the nickel. Right? We change that one to a positive. And then here's the cathode side. And this is what the full drawing would look like. But you add them together, once you change the sign properly, you get 1.03 volts from that cell. Oh, I'm sorry, I didn't see your chats. Oh, yeah, I hate it when that happens. Microphone. Okay, I see. I'll just keep recording. You can look at the rest of the recording. We've covered most of the really essential stuff. So I'll just keep going. I've got a few more slides and we'll be done. Okay, so we've calculated the standard potential for this cell. Now what do they want us to do with it? Nothing. We're going to look at other types of cells. This is a lead acid battery, or sometimes they call it a lead storage battery. And it's made up of the cathode is made up of lead oxide. Lead-4 oxide is the cathode. So that's where reduction takes place. And the anode is made up of pure lead. And they're both submerged in sulfuric acid. That's known as the electrolyte. Oh, they didn't bother to go through give you the half cell reactions. But the cathode side, lead oxide, I'll just draw it up here. So at the cathode, you have lead oxide plus sulfuric acid. And that yields lead sulfate plus water. Okay, let's see if this is balanced. Sulfate, H2O2. That's balanced. And then the anode is pure lead plus sulfuric acid yields lead sulfate plus hydrogen. Okay. So we're not showing any electrons here. So what electron movement is there? Well, this is -4, so this has to be a +4. And this is -2 here, so this has to be a +2. And this is a +2, but this is a 0. Right? So to go from here to here, you gain, you lose 2 electrodes, 2 electrons per lead. And this one, you gain 2 electrons per lead atom. So 2 electrons are transferred in this reaction. Now, what's the voltage? Well, let's see. I might be able to find it if I look back really quick and look at those tables. It might have it. I can read fine print. Lead oxide, 1.69. This is 1.69 volts. And this one is, let's see, we're going to go backwards here actually. Lead sulfate to lead. There it is, 0.35 volts. This is the standard reduction potential. So this is negative, right? Yeah, negative. So the voltage that we need for this one is positive 0.35 because it's running the other direction. So 0.35 and 1.69 is 4, let's see, plus 1.69 equals 402, 2.04 volts. That's the standard cell potential. And all we need is for sulfuric acid to be 1 molar to give you that potential. That's pretty concentrated, right? The acid in these batteries is concentrated. But you get 2 volts per cell. Now, how do you get 12 volts out of a 2-volt cell? Well, it's physics again. If you put these cells in series, oops, you only need 3. So this is 2 volts, this is 2 volts, this is 2 volts. No, you need more. Sorry. 2 volts. 2 volts, 1, 2, 3, 4, 5. 2 volts. And you connect them in series, right? Right here. There's your meter. And you just connect them in series like that. Then the total voltage is the sum of each of those 2 volts. So 6 cells times 2 volts each is 12 volts. That's how you get 12 volts out of your car battery, with each cell only making 2 volts each. You can make them bigger than that, like tractors and diesel trucks often have 24-volt batteries. Marine batteries sometimes are bigger, 24 or 48 volts. You just stack more cells together in sequence. So this one's pushing at 2 volts, and then it adds 2 more volt push, 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 push. Add them all together. So that's the lead storage battery. It's a very, very high voltage cell. Very few cells will give you a higher voltage than that for individual cells, which is why it's so popular. Plus, lead is cheap. Sulfuric acid is cheap. Sulfuric acid has been known for centuries, and then lead for almost as long. The problem, of course, is that lead is not called plumbum for nothing, right? Plumbum is Latin for heavy. Lead is heavy. So it's not well suited for electrical vehicles. It's okay to start your engine and to run your accessories and be a storage point for energy. But lead storage batteries for electric vehicles are not the way to go. It's just way too heavy. The power density is not enough. That's why lithium-ion cells are more useful, because you can get more power out of a lighter battery. And that just stands to reason. Look where lead is. Lead's way down here. It's got 207 atomic mass. Lithium is up here. It's got 6.9 atomic mass. So for the same number of electrons moving, you got a lighter battery. Anyway, other types of batteries we call the dry cell battery. The anode is this zinc shell right here. Right? So every dry cell battery that you buy across the counter, D cells, C cells, AA's, AAA's, they have this same design where they have the zinc here as the anode reaction, and then the cathode reaction takes place in this pasty matrix here. And the carbon rod in the middle is just a conductor, right? It doesn't participate in the reaction, but that is the cathode. All right, so the cathode reaction means the electrons enter through the top and they go out here like this, and they exit through the bottom. Okay, so the negative end of your battery is the bottom side, the side that you push against the spring. And then this top nipple is where the electrons go in. But it's a weird fluke of the development of study of electricity, that when you express current, current is expressed in terms of movement of charge from positive to negative. See, they got it backwards, but we're sort of stuck with it. In chemical terms, the electrons are actually carrying the charge. They used to think that the positive charge was the carrier, but it's not. It's the electrical, it's the negative charge. So we know electrons are moving that direction, but when you express it in physics formulas, the charge goes that direction. Okay, I'm getting close to the end here. Let's see. Look at my hard copy. Other types of the mercury battery. It's not used much anymore because of the obvious contamination, but it still functions. The fuel cell. That's like the holy grail of electric vehicles, because a fuel cell will run as long as you can provide oxygen and hydrogen. Right? And since you get oxygen from the air, all you need really is a supply of hydrogen. So that's the problem, because our infrastructure is built in this country on fossil fuels, not hydrogen. We would have to completely revamp our infrastructure in order to accommodate hydrogen fuel cell powered vehicles. But it's a simple reaction. Hydrogen combined with oxygen yields water. That's it. And it operates at very high temperature. That's another problem. So it produces steam. But it's very efficient, and it has endless supply of energy as long as you've got a tank of hydrogen and oxygen to supply the fuel cell. It works like a galvanic cell. In fact, Apollo 13, when they had their mishap in space, they were actually instructed to stir the tank, they say. So you add a little heat to the tank, and it keeps it stirred so you don't get separation of liquid and gas, and stratification of temperature regimes. And when they did, a manufacturing error in the stirring circuitry ignited the oxygen tank, and it blew a hole out of the side of their vehicle. So not only did their fuel cells not work, they were running out of oxygen to breathe. But those fuel cells, they operate at very, very high temperature. I don't know exactly what it is, but you can't touch it. Now, technology has advanced to the point where we reduce the temperature, but they still operate at pretty high temperature. So you've got to take that into account also. And then there's the storage of the hydrogen. How do you store hydrogen? It's a gas, right? You can't store it as a liquid because that takes too much insulation. And it's a cryogenic liquid. In other words, if you don't have a refrigeration unit there to keep it cold constantly, then it will gradually build up pressure in the headspace and blow the top out of your tank. So you have to have relief valves. So if you just let your tank of liquid hydrogen sit there, eventually it'll all be gone. So we need another way. Pressurized tanks, right? They're pressurized at 2,000, 2,500 pounds per square inch. Right? That's dangerous, especially in a car wreck. So we need some other way. Well, one way that's been proposed is you fill those tanks with a matrix. a metal matrix, spongy metal, and what happens is the hydrogen forms a coordination complex, or actually a compound, with the metal, a metal hydride. And the head pressure on that is much, much lower. It's just enough to supply the fuel cells. So if you open the valve, it comes out slowly. So that's one way around it. So let's talk about corrosion. Corrosion is a natural occurrence for pure metals in the environment. Pure metals are reactive in this oxygen environment. So their natural state is to be the oxide of the metal. In fact, the ores, most ores, not all, but most ores of metals that we want to purify, want to refine, are oxide compounds, like iron ore, Fe2O3, or bauxite to produce aluminum. That's where they want to be. That's lower energy state. So to purify them, and the process of converting, of going from the pure iron to that, or the pure aluminum to that, that's not a balanced equation, of course. That process is corrosion. So the metal is oxidized, right? It goes from 0 here to 3+ here, 3+ there. So that's oxidation. It loses electrons. Now, the rusting process can happen at the surface of a metal, at the surface of iron or steel. All you need is a solution for conducting the charge, and you set up a galvanic cell right there on the surface of the metal. So this forms a pit here as the iron is consumed and deposits rust out here. Now, the big problem is with rust is not just conversion to rust, but it's the fact that the density of rust is much greater than it is for iron. So as you form this rust, it tends to balloon in volume. And you'll see in any old car or some a steel or iron metal implement that's left out in the weather, eventually you'll see it flake. You see flakes coming off of it. That's what happens. As it expands, forming rust, it flakes away. And what that does is exposes fresh metal underneath. So that's why iron rusts so fast. It exposes new metal each time. And as long as that flaking goes on, that metal implement will eventually just completely rust away to nothing. Whereas with aluminum oxide and other metals, actually aluminum is more reactive than iron. So what it does is it reacts so fast that if you have aluminum metal surface here, then it will form aluminum oxide on the surface. And it happens so fast that it seals the underlying metal and keeps it, it's not exposed to the environment. So it doesn't corrode any further. That's why if you throw an aluminum can out in the environment, 100 years later, most of it will still be there because it forms that protective layer. Whereas iron won't do that because it flakes away. Chromium will also do that. So that's why iron and chromium mixed together makes stainless steel. And originally, stainless steel was 35% chromium. I think they can do it with less chromium now. But what happens is chromium is so reactive, it does this same thing. It forms that chromium oxide skin on the stainless steel. And it happens so fast, you just scratch the surface, it's already fixed. And that seals the underlying metal from further attack. Okay, ways that we prevent corrosion. I've already mentioned one of them, alloy. So when you alloy a metal with a more reactive metal, that reactive metal forms a protective reaction like this or like that. Most cars used to be made of steel in their exhaust system, like steel pipe. But that pipe would rust away pretty quick. So they experimented with other alloyings and found that stainless steel was a little difficult to work with. It's very hard, plus expensive. So they experimented with other metals, and they came up with aluminized steel. So you just make an alloy with aluminum and steel, iron and carbon, and it serves the same purpose as stainless steel, but it's easier to work, and it's a lot cheaper. So your tailpipes last a lot longer now because of that. Another alloy, zinc, that you can mix in with other metals and avoid the effects of corrosion. But zinc is more commonly used as a plating. It's a coating. We call it galvanizing. If your parents or your grandparents still have some old buckets around, the steel bucket used to be galvanized. They just take the steel bucket and dip it in molten zinc, and it would coat it with zinc, and the zinc would react with the environment and form that protective layer. So a fresh bucket bought from the hardware store is going to be shiny. Once you leave it outside, start using it some, it gets dull because it's forming that zinc oxide coating. Before it does that, you'll notice that it's got kind of a grainy pattern that goes this way and that on the surface. That's just the way zinc forms its crystal lattice as it coats the surface. My PhD is in agronomy, crops and soils. And I've heard stories of researchers years ago that would set up, they would try to grow plants in the greenhouse to control the environment and study how they reacted to fertilizers, and they analyzed the tissues and all that. But they would grow their plants in galvanized buckets. And they very often they ran into this problem. A certain toxicity was showing up in their plants, some plants more than others. And when they analyzed them, they found that the plant leaves were loaded with zinc. The zinc was leaching into the soil, and the plants were picking it up, getting too much, and it was damaging the plants. So another way of protecting from corrosion is cathodic protection. Very often when steel tanks were buried in the ground, like gasoline tanks, they were made out of steel, they would rust over time. And that would be a bad thing because you release all the petroleum into the groundwater. So before the advent of plastic or fiberglass tanks, what they would do to protect those steel tanks was they would attach them to a more reactive metal. Right, here we go. So there's a pipe, worked steel tank, same. You attach by a conductor to this magnesium, which is more reactive than iron. And what it would do is it would act as an anode, and the magnesium would corrode. It would convert to magnesium 2+ ions and send the electrons up this wire into that pipe. And that would drive the reaction. The natural oxidation of iron would drive it backwards and maintain iron as the pure metal. Actually, this is 3 plus. So this is me, 3 electrons. And by supplying those extra electrons at a voltage that's higher than the reverse for this, then they would maintain those tanks as uncorroded steel. That's known as cathodic protection. I never made sense of that. The protection is actually being supplied by an anode. So why don't we say anodic protection? Well, choice of terms, and I don't have anything to do with that. They also do this type of thing on ocean-going vessels, ships. If you have a chance to go down to the docks and look at ships that come in, after they've been unloaded of their cargo, they'll of course rise in the water. And sometimes you'll see exposed around close to the waterline a belt, which is metal, around the hull of the ship. That metal is made out of pure zinc. Zinc is more reactive than steel. So it does the same thing. It provides electrons to the steel hull of that ship so it won't corrode. Now what they'll also do is they'll put an electrode into that zinc strip and supply a trickle charge of electrons. So it'll protect both the zinc and the iron in the ship, as long as there's power supplied to it. But if in the docks they have to shut their engines down, they have to shut their generators down, then the zinc will take over and provide until the power comes back up and they can trickle charge into the zinc as well. But that's how they protect their hulls. Now here's electrolysis. Right, we're going to run the reaction backwards. We've already talked about that actually. Anti-corrosion effects are electrolytic. That is, we drive the reaction backwards. The iron wants to go this way, but we drive it this way by supplying that voltage that's higher than the oxidation voltage. So what's the stoichiometry of electrolysis? Well, you need to know what the current is, and current is measured in, let's see, hold on a second. Current is measured in amps. And an amp is equal to 1 coulomb of charge per second. Right? So at a stationary point, if a coulomb of charge at 96,000 well, that's for a mole of electrons. 1 coulomb is a charge. If 1 coulomb passes that point in 1 second, that's an amp. 1 amp. How long is it supplied? Well, if it's supplied for 60 seconds, that's a minute, right? So 60 coulombs went past that point. And then you can convert coulombs into moles of charge, moles of electrons. Right? Once you know the total coulombs, then you convert it into moles of electrons. Now you're into chemistry, stoichiometry. And the moles of electrons then, depending on how many are required to produce the electrolytic reaction, are converted into moles of the metal. And then you can convert it to mass simply by molar mass of the metal. Okay? So those would be the steps for determining how many grams of a metal can be deposited by this electrolytic process. Okay? Okay, there's your amps times seconds equals the quantity of charge. Then you convert it to moles of electrons, and then you convert moles of electrons to how much metal that is, and then metals to mass. So here we have a question. There's an unknown metal that we want to electrolyze. In other words, change the ion into pure metal and deposit it. So the conditions are, over this course of 52.8 seconds, with a current of 2 amps, which is pretty high actually, and we were able with that to plate 0.0719 grams of the metal. From this solution, we plated that much metal out. What is the metal? All right. Solve this problem backwards. If we want to find out what metal it is, we need to know something about that metal, right? We can't know the atomic number, right? The data will not supply that. But we can know the atomic mass. And if you know the atomic mass, more often than not, you can find it on your periodic table. So we need moles, grams per mole. That's what we're looking for. How many grams per mole? Okay, we know the solution is MnO3 taken 3 times. What does that tell us about the metal? This is a minus charge. So you have 3 minuses. This has to be 3 plus, right? So that means this metal with a 3 plus charge has to get 3 electrons to give us 1 mole of pure metal. So there's your stoichiometry right there. Now, how many moles of electrons are transferred? Okay, let's go up here. Moles of electrons. So we've got, how long does it go? 52.8 seconds. Right? How much charge is that for 2 amps? 2 amps is equal to 2 coulombs per second. Right? So there the seconds are canceled, and you got charge in coulombs. Now we need to convert coulombs to 96,485. Coulombs per 1 mole of electrons. Okay, now we got moles of electrons. So how many moles of electrons per mole of metal? Three moles of electrons for 1 mole of M. Okay, that'll give us moles. That'll give us moles of that metal. So I just need to pull out my calculator and say 52.8 times 2 divided by 96,485 divided by 3, which is 3.65 times 10 to the minus 4th. 3.65 times 10 to the minus 4th mole of metal. Okay? How about mass? We're given mass, aren't we? 0.0719 grams. 0.0719 grams per 3.65 times 10 to the minus 4 moles. That will be the molar mass of our metal. Let's see, 0.0719, and I want to divide that by this number. And I got 197. Grams per mole. Okay, let's look on our periodic table. Let's see, we can follow it along, get bigger and bigger and bigger and bigger and bigger and bigger. Let's see, keep going, keep going, keep going. 196.97. gold. We're gold plating something. Okay? And that's an efficient way to gold plate something like this. You don't want to use a lot of gold, but you want the surface to be protected with the gold. And if you do it this way, then you can take a bar and probably produce tons and tons of product, simply gold plating it. Okay, so the slide is animated to give you these values and goes through the calculation. Here's the stoichiometry I talked about before. And then we do the calculations, convert, and then calculate the molar mass, and there it is. Let's see, is there anything else? Yeah, we've got a couple more slides. Okay. All right. So, what if we have a solution that contains 0.1 molar of each of the following? Lead, copper, tin, nickel, and zinc ions, all of them. Predict the order in which the metal plate out as the voltage is turned up from 0. Right? So if we have those in solution, then what we need to do is supply enough voltage so that the reaction will run backwards and plate out metals from each one. Right? We want to have this one. Like that, and the rest of them just like that. Well, which one's going to plate out first? Well, as we increase the voltage, we're going to exceed their reduction potential. And each time you exceed the reduction potential, that one plates out. Right? So what we want to do is, well, to answer this question, do the metals form on the cathode or the anode? Well, the cathode is where reduction takes place. So they're going to form on the cathode, right? Okay. So let's look at it that way. The cathode means we need reduction potential. So the more positive the standard reduction potential is, plate first as the voltage is increased. So they'll plate out in this order. All right. So all we have to do is, since we're running the voltage backwards, the less reactive metal will plate out first, and the more reactive will plate out last. Okay, so what are some examples of how do we use electrolysis to make money? Well, definitely production of aluminum. Back in the late Middle Ages, aluminum was more expensive than gold because it had to be produced chemically. I mean, by mixing stuff together. Right? In the beginning of the 20th century, a kid, whose last name was Hall, I believe, figured out how to produce aluminum by electrolytic processes. And then it became really cheap. Aluminum wasn't always that cheap. I mean, you couldn't afford to make aluminum foil and wrap your food in it and then throw it away when you're done. Or wrap your turkey or whatever the case may be. But the production of aluminum is an electrolytic process. Purification of metals, right? When the when a mining company produces copper, they may do some initial refining on site or very close to the site of the mining operation, and they may produce something that's 95% copper. That's not good enough, not even for electrical wiring. It needs to be 99.9% copper to be functional as electrical wiring. So what they do is they take the copper supplied by the mining company, and this may be in the same company. They send it to another facility, and they electrolyze the copper. In other words, they convert it into copper ions and plate them out on the cathode. And then when they do that, you've got 99.99% pure copper. We can plate with it, right? In the old days, we didn't have plastic bumpers with shock absorbers built in. We had big, heavy steel bumpers. I mean, they were monsters. They were probably at least a 1/4 inch thick steel. But they looked ugly if you let them rust, so we protected them. We coated them in chrome plating, and they still do that on antique vehicles. There are companies that will chrome plate. And the same process. You just reduce the chromium ion onto the bumper as the cathode. Electrolysis of sodium chloride. Right? You take sodium chloride and melt it, run electricity through it, and you get sodium metal and chlorine gas. That's where the chlorine comes from for a bunch of other reactions. We make bleach out of it, for instance. And you take sodium metal and dissolve it in water, and you get sodium hydroxide. Right. So here's the Hall process. It was modified by this Frenchman. But the molten aluminum, you have to melt this, right? You can't put it in solution. You can't put it in water solution. It doesn't work. You have to melt it to make the ions mobile. And if you try to melt, let's see, I've got it around here somewhere. If you try to melt aluminum oxide, pure aluminum oxide, you got to get the temperature up to 2072 degrees Celsius. That takes a lot of energy just to get started. So Hall worked with various mixtures, alloying, not really alloying, various mixtures of compounds, and he found that if he added cryolite, which is a naturally occurring mineral. Let's see, got 6 of these, that one, and 3 of these. This mineral, sodium aluminum fluoride, you mix it with it, it reduces the melting point down from 2072 to 960 degrees Celsius. So these two together will now melt at 960. So that's more efficient. You can put up to 10.5% of aluminum oxide in this mixture, and then you can run your charge through it and reduce aluminum from the process. You're reducing this one, and you're reducing some of that too. The nice thing about it is pure aluminum is denser than this mixture. So as you form the aluminum, it just sinks to the bottom. And then at a certain point, you just knock this plug off and drain out the pure aluminum. right out the bottom. And the carbon electrodes are part of the reaction. Right? The carbon electrodes are actually converted to pure carbon, converted to CO2. So that's what all the bubbles are. That's carbon dioxide formed from the carbon electrodes. And you have to replace those periodically. But graphite is cheap. One other thing that you need is a massive supply of electricity. And it needs to be cheap. So coal-fired power plants are very efficient and produce electricity rather cheaply. Hydroelectric production of electricity is relatively cheap, mainly because the government builds most of the dams. So they just write it off to the taxpayer and then sell the electricity dirt cheap. So you'll find processing plants in areas where there's plenty of coal, like southwestern Pennsylvania, or there are even some places around the Great Lakes. That's more for logistics than it is for coal. And on the Tennessee River Valley, right, they've got lots of dams in there. So Alcoa set up operations in all three of those locations. And that's good, right? Because what's the cheapest way to ship anything worldwide? On water. Put it in a ship, send it. Relatively cheap to send stuff anywhere. So they get this bauxite refined to a certain point at the mine. And most of the bauxite mines are in tropical areas for environmental reasons. I mean, what happens is you get so much water over the centuries, it just drains anything that's soluble out of the soil. And what are you left with? Well, mostly aluminum oxide and iron oxide. So you find the deposits where you have high aluminum oxide and mine those. And just clean them up, and you have mostly aluminum oxide. Throw it on a ship, say in Puerto Rico, and send it up the eastern seaboard. You go in the St. Lawrence Seaway, go down to the Great Lakes, and dump it at your whatever site. Or you go up the Mississippi River, and then up the Ohio River, and up to Pittsburgh and that area, and dump it there. Or you can go down from the Ohio River, you can go down the Tennessee River into the Tennessee Valley, and they have processing plants there too. So that's how we got cheap aluminum. You can electroplate spoons, right? Add silver to your spoons. Do that. Actually, you can clean the corrosion off of your silverware simply by taking your corroded silver, and in a baking dish, line it with aluminum foil, and then throw some salt in there as a conductor. And put your spoons, lay your spoons, and make sure they contact the aluminum. And they will convert the silver corrosions, which are usually silver oxide, silver sulfide is more common. They will convert that, they will electrolyze it. The reaction, actually, it's a galvanic cell. They'll convert that corroded silver back to silver metal, and you'll have shiny silverware. And here we're electrolyzing molten sodium chloride. So you arrange your apparatus in such a way that when the chlorine gas forms at this electrode, it's just vented out. And over here at the cathode, you get sodium. And the sodium metal is delivered. I'm not sure if sodium is lighter than sodium chloride. Oh, here again, it takes a lot of energy to melt sodium chloride. So if you add a little calcium chloride to it, it decreases the melting point. And apparently, if your voltage is adjusted correctly, you simply reduce the sodium and you don't touch the calcium. Okay, that's it. I'm done, and I'm I'm way past time. Almost an hour past. Okay, so that's it for Brown Chapter 20, Electrochemistry. And next week, next Friday, we'll have a review on this. And then the following week will be finals week, and you can take the exam at your leisure. As long as it's in by Friday, because I have to turn the grades in on Monday. Okay, that's the end of that, and we'll see you next week.